Okay, so welcome back. So this would be the last module for the second week, and so we'll continue our discussion in terms of those data collection and all that. And one of the major thing in this particular module is we will try to solve some problems, isn't it? Many of you might be engineers or even science people. We always like numbers. So we like numbers. We use numbers, and so let's all this stuff that we said we will have to collect this number and we have to collect that number, but how those numbers are relevant. So we'll talk about some of. I'll give you some math problem. I will solve I think 1 or 2 problem on this video. I'll walk you through the solution, but then I give you some questions and I also tell you how to solve it, and we'll go over that. And then my encouragement to you will be to go and solve it by yourself. We'll see if we can. We'll try to provide the solution. Not right now, after the 4th week, but right now I want you to. I'll post it as a PDF on the website. But right now, I would encourage you to practice those problems by yourself, because unless you do it, what happens these days? If I give the solutions to the students, they just try to memorize the solution. Those of you who are planning to take the exam, and then memorization is not going to help you. You need to understand it. That's why I want you to solve it first, and then if you're not able to solve it, ask question to us on discussion forum. We'll be more than happy to give you some hint, try to give you some directions on how to solve it. If you are confused in doing that, we will be more than happy to do that. So okay, so let's start with some this is a concept again which we use in terms of risk assessment and all that. It's a bioconcentration. Now what is the bioconcentration? We talked about just before that how the concentration will be measured in the water phase. Now so many of these chemicals from the electronic waste, especially say if you have the mercury in the methyl mercury phase, some of these organics chemical which is present, they have a tendency to accumulate in the aquatic animal such as fish tissue. Now when say a chemical has those kind of property to accumulate, they have to be lipophilic. Like you may have heard the term hydrophobic, hydrophilic. Phobic means what? Phobia. Phobia means they are afraid. So hydrophobic means what? Something which is afraid of water. Something which is afraid of water means what? Something which is afraid of water means it will not be soluble in water. If something which is soluble in water is trying to have party with water, like really they love water, then it's a hydrophilic, because it has the affection for water and it will be soluble in water. But hydrophobic will be not soluble in water. So that's on the water part, and that is also important. Here when we are trying to talk about bioconcentration, we are talking about very same concept, but here we are looking at lipophilic and lipophobic. Now what is that? What is lippy, like lipophilic? What does that mean? It's phobia for lipids, the fats in the body, and affinity for the fats in the body. Now if contaminant, if it has a affinity for fats in the body, it will go and accumulate in the body, isn't it? It will go into our fat and then try to be accumulated over there. If it's phobic, it will not accumulate. So it will just go through the system. It can come out in the fecal matter, will come out in the urine and all that. It will not accumulate. So the effect, the adverse effect will be much less. Is something which is lipophilic will accumulate, and then it will try to react with all those our internal stuff, which I don't know much about. It's a medical science, but that's how once they accumulate, they start creating trouble for different organs in the body. So this is so in terms of how much up to what level it will accumulate. So we do calculate many times. We have this equilibrium concentration of a chemical. We try to have this equilibrium concentration of a chemical in the aquatic animal or aquatic species. We can estimate by multiplying the chemical concentration by a bioaccumulation factor. Like what is that bioaccumulation factor for those particular for that particular organic chemical? So for example, like if you want to know concentration in fish for a particular contaminant, you know the concentration in water, and then you multiply by bioconcentration factor. So you take the average concentration in water, multiply it by the bioconcentration factor. That gives you an idea of what could be potentially the concentration in fish. Now from the concentration in fish, if you and I consume that fish, I'm right now you are watching this video, which have been recorded at IIT Kharagpur, West Bengal. People love fish here, so as from Kerala and several other parts of India, and of course abroad. So if things gets this bioaccumulated in fish, people who love fish, people who eat fish will get exposed to that, and that's true for other food items too. So that's how we can get potentially exposed. So we do calculate, that's the bioconcentration, or this concept of bioaccumulation is a very important concept in terms of looking at the environmental risk and human health risk from electronic waste, essentially the chemicals in the electronic waste, which is a problematic. So let's look at some of the drinking, some of the examples. Let's try to solve an example here. Now, as you can, so there is a simple example. Say if you have a drinking water which is disinfected with chlorine. This is we use chlorine. If you have taken water treatment class, you know that chlorine is used as one of the disinfectant. Then we do have we also leave some residual chlorine. But one of the problem with when we add chlorine is it produces an undesired byproduct, which is a chloroform. Many of these, you may have heard the term disinfection byproduct. So disinfection byproduct, which is a term used for these kind of product. So when it is disinfected with chlorine, we get a byproduct chloroform. And say now if there is a chloroform is there in the water, we are consuming that chloroform. So chloroform will have certain adverse effect to our human body. So now taking a scenario that suppose a 70 kg person drinks 2 liters of water per day for 70 years, and which has a chloroform concentration of 0.1 milligrams per liter, because he has been taking that water from a drinking water plant. The drinking water plant was to have a disinfection with chlorine, and of course these days we are actually trying to not to have chlorine and go for UV and other stuff. But if they have a chlorine and you have this chloroform being formed, average concentration of chloroform over that 70-year period is say 0.1 milligrams per liter. So with that data, we have to find the upper bound cancer risk for this individual, as chloroform is a carcinogen. And if the city has 500,000 people, they drink the same amount of water, how many extra cancer per year you can expect? Assume the standard is we have 70-year lifetime as the standard. And then if you compare the extra cancer per year caused by the chloroform in drinking water with the expected number of cancer deaths from all causes, the cancer death rate in, for example, in US has 189 per 100,000 per year. So we have a potential factor is also given to us for that. So we have been given what is the total cancer death that is happening in that particular country, and then if you look at the extra cancer that is done from this chloroform, we can put these things in little bit in perspective. So with that particular data, now if we try to approach the problem, and so first of all we will try to see that CDI calculation that we did earlier, that's which was average daily dose divided by the body weight. So it's you can find out. So that's average daily dose divided by the body weight. It was 0.1 milligram per liter was the concentration, and so we are working on part 1. So 0.1 milligram per liter was the concentration, 2 liters per day divided by 70 kg. So that if you look at this number, you have liter will cancel out. So you have milligram per kilogram per day. So that's your average, it's a milligram per kilogram per day. So that's what you will see in terms of, so we have the units seems to be okay. So we got this number 0.00286 milligram per kilogram per day. Now if you take the CDI and multiply it by the potency factor, which was given to us 6.1 times 10 to the power of minus 3, we can multiply the CDI, which is 0.00286 with that, and then we get total lifetime cancer risk as 17.4 times 10 to the power of minus 6. So that's how we can calculate the total lifetime cancer risk which is there. So over a 70-year period, so in a 70-year period, the upper bound estimate, so probability that a person will get cancer from this drinking water is about 17 in 1 million, because 10 to the power of minus 6 is 1 in a million. 10 to the power of 6 is a million. So, 10 to the power of minus 6 would be 1 in a million. So, out of, so nearly we are talking about 17.4 people or 18 people, nearly 17.4 or 18 people which will have which can potentially get cancer by drinking this water over the 70-year period. So, that is like how we can do this calculation. So, that is the part 1. Now, part 2, there is a 117.4 cancer per million people for a 70-year period that was told to us. Then in a given year, have a population of 500,000. So, for a million people, we have 17.4 cancers. So, 500,000 people, we are talking about 0.12 cancer per year. So, it is not too much, it is not detectable. So, disinfection will create cancer? Probably not, because of the calculation that we just saw. So, total, in terms of the total number of cancer death that is expected in the city of 500,000, we have been given 189 cancer per year, 500,000 people, and then out of then we have 100,000 people. If you remember, let us look at that problem in a minute just to see the data. So, we had I compared the extra cancer per year caused by chloroform in drinking water with the expected number of cancer death from all causes. The cancer death rate in United States is 189 per 100,000 per year. So, that is why we have that. So, we have 189 cancer per year out of 100,000 people. So, if you do this calculation, you get around 945 cancer deaths per year. So, this much amount of cancer death you can expect when you have a population of around 500,000. So, nearly certainly less than 1,000 people will be dying from that particular cancer. So, this is how we can calculate these numbers. So, this is we had the 3 parts in this problem. So, one by one we can calculate these numbers, and this gives us. So, now we know that yes, the potentially 945 death can happen. So, in that case, how to manage now. So, we will talk about, we will have to do some risk management in terms of the managing this risk, so that we can reduce this fatality to in terms of how much people potentially can die from that. So, now in terms of some other problem, like I think we have 3 problems here which has been listed for you to solve. What I will do in this 3 problem is I will just tell you how to solve it, and then once you are doing it in the discussion forum, on the discussion forum we will try to give you the answer, not the solutions. Solutions just before your exam or towards the end of the course, we can upload the solution of this, but I want you to practice. That is why I am not going to give you the solution. So, right now, so say there are 3 problems. Let us look at one by one. Just I will give you a quick overview, so that if you can get the clarification on, say, basically I will try to highlight the things which I think may confuse you, and just try to give some clarity on that. But if you have again any question, put it on discussion forum, we will answer that. So, you have just taken a job. So, this is the problem number 1 which I want you to work on. You have taken a job at a metal plating plant, and some of the metals you work with contain arsenic as impurity. So, not directly arsenic, but some of the heavy metals that you are working with, it has arsenic in them. So, when you heat those metals, it gives off arsenic vapor, which creates an average concentration of arsenic as 0.00002 milligram per meter cube in the air in the workplace. So, it is more like an occupational health and safety question. What is the increased risk of cancer if you continue to work in this job for the entire career? Say there are 220,000 workers in the US in metal casing plant similar to one in which you would work. How many worker deaths above the background cancer rate would be expected due to their occupation? So, if you have the average concentration in the air in the workplace, you wanted to have increased risk of like whether there will be an increased risk of cancer or not. So, it is a what is the you need to calculate that if you work for the entire career. So, you can take maybe 35 years or 40 years. I would say 35 would be a good age, good time period to take for any job, because somebody getting a job of say around 25 years, people retire at 60. So, we are looking at around 35 years, and then we are also looking at, so from 220,000 workers, how many worker death above the background, and we can use the similar approach as we used in the previous example. So, I want you to do that. So, we'll find out the increased risk, and in terms of the people, like what is your like how you will be able to calculate that. So, I want to go ahead and do this problem. And then the second one is, you have the suppose an industrial facility, it emits benzene into the atmosphere, is being proposed for a site near a residential neighborhood. Air quality model predicts that 60% of the time prevailing wind will blow the benzene away from the neighborhood, but 40% of the time the benzene concentration will be 0.01 milligram per meter cube. Now, here, although it is a residential neighborhood, we are saying that 60% of the time benzene concentration will not be high, it is only 40% of the time when it will high. That has to be reflected in our calculation. When we are trying to do that calculation in terms of the impact, that has to be reflected. So, it is only the 40% of the time which is of concern. So, what we need to assess is the environmental risk, incremental risk to adults in the neighborhood, if the facility is allowed to build, and if acceptable risk is 1 in a million, should this plant be allowed to build? That is we want to hear from you in terms of. So, you can put on your discussion forum, let us have a discussion there in terms of whether we should have there is a, and let us see what different people from this class thinks about it, and then we can like as I said, every 24 hours we will try to respond back to you. We will definitely respond back to you. We can respond earlier as well, but within 24 hours it is our goal to respond back to you on any query you have on discussion forum. So, here again like we can have these things going on in a thread, and then I can come back, you look at every 24 hours and give my feedback on what are the different comments that have been made on that. So, that would be interesting. It would be like a two-way conversation rather you just listening to my videos, but I need to listen your voice too. When I say voice, it does not have to be literally voice, it can be even what your thoughts are, what your thought process for this course. See, we are now approaching the end of second week. So, you need to kind of let us know that whether the course you are enjoying, what are the, I hope you are enjoying, but if there is any feedback, constructive feedback which can help us improve it a little bit, that is always welcome. So, please do that. So, in terms of this second problem, what we have to calculate is, say we based on this incremental risk which is going to happen to the like a neighborhood, is it acceptable, is it so that we should allow this plant to be built. So, what's your thought based on the data? So, you need to first collect the data and try to find out whether it's a higher than whether it's a whether it's RFD value or slope factor, and how it compares with the slope factor on RFD. Is it increasing higher concentration than that or lower concentration than that? So, those things you need to do the calculations, and then you will have to you will know whether it's an acceptable risk or not. So, the third so that gives you that example of first two problems. In the third problem, if again it's a 70 kg man exposed to 0.1 milligram per meter cube of tetrachloroethylene, which is TCE, and it is getting exposed at his workplace. If he inhales 1 meter cube per hour, 8 hours a day, 5 days a week, 50 weeks per year, and 30 years, and if tetrachloroethylene has an absorption factor of 90%, and the inhalation potency of this 2 times 10 to the power of minus 3, what would be his lifetime cancer risk, and what the risk had been had a 50 kg woman was similarly exposed. So, rather than 70 kg men, it is a 50 kg woman. So, again most of these calculation how it needs to be done, we have already done in the example calculation that I just showed you, or the other two which I was trying to explain. So, it is if you inhale if somebody inhales 1 meter cube per hour, 8 hours a day, 5 days a week with this much of in terms of adsorption factor 90%, inhalation potency is given. So, we should be able to calculate based on the example that was provided earlier. You should be able to calculate what would be the risk to a 50 kg woman, or what would be the lifetime cancer risk for a 70 kg man. So, in both the cases we should be able to find out. So, I did not give you like a step by step solution for this problem, that is on purpose. I want you to solve it. The previous theory and the solved examples that we showed is good enough for you to do this solution, this problem solving. But again, if you get stuck with something, feel free to put it on discussion board. Say that what is the problem, what is exactly you are having a problem. If needed, we can respond back on discussion board if as early as possible. If needed, we will try to have some extra kind of tidbits of like a small video or something up there as well. So, do not worry, but do try this and try to make good use of this problem. And one place where you can find some of the information, if you are for these numerical problems, chapter 4, which is the risk assessment chapter of the Gilbert Masters book, Gilbert Masters and Wendell Ela, Introduction to Environmental Engineering and Science. So, that particular book does have similar problems there. So, and then they do have some exercises on the problems as well. So, I would encourage you to look at that if possible. It's I guess it's available it will be available in the central library, and of course, possibly in your other libraries in your campus or wherever you are. So, in that, look at the chapter 4, which is the risk assessment chapter of this particular book, and that will help you in terms of trying to understand some of this concept, which we try to explain, but if just in case it will not clear, it will help you to make it more clear from there. So, that kind of brings the end to that, but that kind of discussion that we were having in terms of looking at the fate and other stuff, fate and transport, that kind of gives us kind of closer to that. And then now what we want to get into is looking at how to recover these metals. That is another big area in electronic waste right now. We are producing lots of electronic waste. In fact, the developing country, India, China, they are going to, they have already surpassed the developed country. So, total e-waste produced in the developing country is more than the total e-waste produced in the developed country, because most of the developing country has higher population as well. So, in that way, it helps we have looking at the electronic waste, we are looking at the potential environmental harm and all that. But one of the thing about any waste is a resource. I told you waste is a misplaced resource. So, if we can, and these electronics, they have lots of heavy metals which should be potentially recovered. So, in this case, we are trying to see, like in this particular lecture, we will try to continuation of course, we are now it's in this particular lecture, we will try to look at in terms of how we can do the recovery of metals. What are the things that is needed for recovery of metals for electronic waste? So, let us get started on this particular topic. And so, again, in terms of the introduction, we know that which is the waste electronic equipment, has been taken into consideration not only by government, but also by public due to their hazardous material contents. Currently, the main opposition for treatment of electronic waste are reuse, remanufacturing and recycling, as well as incineration and landfilling. So, recycle of e-waste is an important subject, not only from the point of view of waste treatment, but also from the recovery aspect of valuable material. So, because there are certain rare earth metals which are rare. So, it is very difficult to get them, and only like 1 or 2 countries in the world where you can get those for. So, the question is, can we recover those material rather than going back to the mining site, trying to mine one more set of stuff? Can we recover these material and use it? So, that's thought process is also there. And what is the present situation? It's still a little bit of limited due to the heterogeneity of the material. If you look at the metal content, it's nearly 28 to 30%. Out of that, you have 10 to 20% is copper. So, we can that's why some of the initial work, initially one of the metallurgy professor on our campus also, he focuses on recovery of copper. So, it's can we recover copper? Then lead is around 1 to 5%. Earlier it used to be more, as I showed you some pictures earlier in the earlier video, but nowadays lead is around 1 to 5% in the newer electronics. We have nickel around 1 to 3%. Then we have precious metal like silver, platinum and gold, which is around 0.3 to 0.4%. But if you think about the huge amount of electronic waste, even at 0.3 at 0.4%, these precious metals are really valuable. You can get a lot of let's say precious metals out from these electronics, and that could be a good value proposition in terms of the business here. So, one thing we need to think about that when we talk about this recovery of rare earth metals, it has to be economically feasible, economically sustainable. So, for that you need to have a certain critical mass and of course the technology, so that we can recover this gold, platinum, silver and other, and then we can sell it to make money. That is how it will run for a longer period of time. So, but these are the common metal, like copper is number 1, then we have lead, we have nickel, and then of course silver, platinum and gold, which is you hear a lot about in especially gold, you hear a lot. Other materials which is there, which is plastic, bromine is there, glass and ceramics, which is 49%. Beside this, we have some electronic inorganic elements, some other organic compounds are there in circuit boards like isocyanides, phosgene, acrylic and phenolic resins and all that. So, those are also present over there. So, in terms of the recycling, let us look at the big picture recycling in this particular, and then we will go into nitty-gritty detail in the next video, which will be the video of week 3, the first video. Right now, we are in the week 2 last video. So, if you look at the recycling of e-waste, that is the essentially this is what is happening. You have you can do disassemble, and in India, although a lot of formal recyclers are coming up, but unfortunately the way the system is working right now because of implementation issues, and that is what we have been talking many times, even when I go to certain meetings, ministry meetings as well. We have very good rules, probably one of the best rules in the world. We have the technology know-how. I am talking about in general, not only e-waste, municipal solid waste, so or any of these plastic waste, biomedical waste. For all these waste stream, we do have the rules is good enough in terms of environmental teeth, may not be from implementation point of view. Of course, we can debate whether it is implementable or not, whether we do not have the infrastructure to support it. So, and then sometimes it is implementable, sometimes it is not, but we can it is a case specific, there cannot be a blanket statement there. So, but in terms of e-waste, specifically for e-waste, the most of the e-waste collection and management in developing country, including in India, is still being done by informal sector. So, the informal sector is what is they are getting the electronics, they are trying to dismantle, they are trying to get the material out. So, what they do is the disassembly is done by any whether it is a formal, informal, disassembly is done. Once it is disassembled, some companies what they have is they try to say if one particular unit may be bad in that particular computer, but you get several other computers. So, between you can other like 2-3 other computers, you can salvage enough components to make it a brand new computer, and so it is not brand new, it is a refurbished computer. You make a refurbished computer, and then if you want, you may want to sell it too. So, that is it's done. So, disassembly is done, then you may have to do, you can do some upgrading as well, you can do the refining, and but ultimately what we are trying to do is a disassemble, then you try to put the metals and other stuff in that particular market, then your circuit board, which is the core, that you try to refine. So, you try to use the circuit board to refine, and basically it is a refinery. So, it will be an e-waste refinery, and then you try to get the material out from there. So, a flow chart how the material is option for recovery of metals. So, it starts from e-scrap, then you do the manual dismantling, there is a size reduction, then there could be a physical separation, hydrometallurgical and pyrometallurgical stuff or electrometallurgical stuff to get the base in precious metal like copper, gold, silver and palladium and all that. So, this is a typical schematic for options for recovery of metals from the e-scrap. So, this is how typically it works, and so in terms of let's I think stop here. So, so that we will get to this, we will start from this slide again in the next video, and we will go over the process description, existing e-waste recycling technique and all that, what are the different techniques, how we use them, what are the pros and cons of using those different techniques. So, in this particular video, what did we learn? I am trying to summarize this time in every video. At the end, I am trying to have a summary that what we learned in this particular video, because at the beginning I am telling you that what you will learn in this particular video, and at the end we should see whether we really learned that or not, and what should be the follow up. See, all these courses that we are offering, it is only to generate interest. These things are lifelong. Electronic waste, you take this 4-week course, that doesn't mean that you don't have to look at electronic waste after say a year or two, because things keeps on evolving. The market becomes so dynamic, type of waste is changing, types of products are, of course products are changing, that's why waste is changing, composition is changing. So a lot of things are happening today. So in terms of this particular video, what we tried to do in the, as I mentioned in the beginning, the goal was to expose, first talk about this bioconcentration concept, which we did. Then we talked about, we worked through a solved examples of how we do some of these calculations in terms of getting this different factor in terms of exposure, duration, whether how many people can potentially get sick, potentially get cancer and all that. So we did one problem, we walk you through a problem, then I have given you 3 problems to work on. So please do that. And then we started talking about recovery of heavy metals, recovery of precious metal, and we are kind of just in the middle of that. So we'll continue this discussion in the next video. This is where we start, and so that will be the week 3 material. So week 2 material ends with this particular video. So again, thank you. It is halfway done. This is a 4-week course. 2 week is done. 2 more week is left. I hope you are enjoying it. Again, any feedback, I will like to hear from you through the media of discussion forum. Thank you.